So my name's Mike, and I've been working on Chrome for about 3 years now. And I work on all parts of the internal, so mostly on the back end. Touched plugins a little bit early on, worked on some networking related things, a little bit of JavaScript integration, and so forth. So ultimately what a web browser does is it takes some set of content and it's going to render it on the screen. Most commonly that's HTML. So there's nothing particularly tricky about that. It's been done for many years. But when we invented JavaScript, the whole point of JavaScript was so that people could dynamically change what that page looks like without having to change statically the content. So in order to do that, you have to come up with a set of APIs. And those APIs are what we call the DOM, the Document Object Model, and it's the API that's available to JavaScript for changing the content that's being rendered. Most web pages today use a fair amount of DOM bindings, especially the kind of Web 2.0-ish. Gmail certainly uses it a lot. Documents, spreadsheets, things like that. But pretty much, all the major web pages use it in some form, whether it's being displaying a little stock ticker or displaying advertisements or what have you. Everybody's got some amount of JavaScript. So a lot of times we talk about how JavaScript is fast, and Apple's got some great benchmarks. We've got some benchmarks for measuring JavaScript speed, but generally what they're measuring is just how fast the JavaScript engine is. So the second part of JavaScript is actually modifying the UI, and that's where the DOM comes in. So you use JavaScript to modify the UI. And then there's two halves that become important. A, how quickly can you run your JavaScript? That's critical. And then B, how fast can you make those API transitions to and from out of JavaScript and into the browser. The browser is usually written in C++, all the major browsers are. And of course your JavaScript is in JavaScript. So you've got two very different programming languages and you're transitioning back and forth between them. And that's what improving DOM performance is about. Well, ultimately, we're just trying to make web pages run really fast. When web pages were static, that didn't involve JavaScript. It didn't involve bindings. But of course, we're long past having static web pages. So application programmers today, they're building very sophisticated things inside of JavaScript and HTML. And they need that to run just as fast in the web as it would run on a desktop application. So a lot of times you're constructing a user interface based on dynamic data that's changing, based on user inputs, based on stuff you're downloading incrementally off the web. And they'll use JavaScript as the glue to inject it into the user interface. So the performance goal for us is to just make sure that web pages run really fast, that users have a really good experience. If it takes a long time to add 10,000 rows to a table, well then the user's going to be sitting there waiting, and users don't like to do that. So we just want to make these applications run really well. Right, so we started out with WebKit, which is a pretty nice rendering engine for web content. That comes from Apple. They did a fantastic job of optimizing a lot of the CSS patterns and things that people are doing. One of the things that we changed, although they had a good JavaScript engine, we thought we could do a little bit better with V8, so we came out with V8 instead. But when you change the JavaScript engine, the interface between the JavaScript and the C++ side all changes. So there's some elements that are common. The DOM API itself is exactly the same whether you're using either browser. At least that's our intention. But we need to re-optimize all those code paths. And because we do things differently in V8 to make it go fast as a JavaScript engine, that does have effect on how we talk to the browser. So some of the things that we ran into are simple things like just converting strings way too often. You start out with a string in JavaScript, and then you've got to use that string on the C++ side. It sounds so simple. And yet so many projects run into trouble with just string conversions, and it really does add up. Other things, when you're dynamically creating lots of nodes, you need to be able to create them really fast, and so we found ways that we can cache the templates of what a node should look like. So the first time it's created, it's a tiny bit slower. I mean, we're talking about sub-millisecond here, right? But when you add them up in terms of the way people are doing it, thousands and thousands of times on a web page, it matters. Also looking at the way events fire. So a lot of times people have a large, complicated web page, and they have a lot of different things that can change. So they're monitoring for events all around that page. And we need to make sure that the browser doesn't get slow when there's too many event handlers being registered and things like that. we put in this new spiffy JavaScript engine, and in order to do that, we had to completely rewrite the mechanism where for how you communicate between JavaScript over to the web browser. Probably the biggest difference between V8 and the other JavaScript engines is that V8, the garbage collector, we use handles to reference everything rather than reference counting. And that's a very big shift. So suddenly passing strings between the two environments becomes very difficult. And I say strings, but it's actually any piece of data that you want to pass between the two. In the kind of the old model, you could reference count, and you could pass those straight across, and you can build a couple of very simple mechanisms where data just passes very cleanly. And that's the advantage of the old model. But that old model didn't have nearly as powerful of a garbage collector. The garbage collector in V8 is extremely important because if you're going to run complicated JavaScript applications, you need it to be able to just run in the background. You don't even notice. And so you'll hear the V8 team talk about GC pauses. And they want to be able to animate these complicated things, and literally you never see it stop. Whereas in a browser that's got a heavy garbage collector, you'll see it kind of go, and then go, and then go. So because we made this shift from a completely reference counting model over to this new model, which is, it's handle based and it's its own collection of memory space separate from the browser. We lose some of the ability to just share these things back and forth fairly seamlessly. So we had to optimize it a lot. So you could actually call it just a bug in Chrome 1.0, I suppose. It's a place where we weren't as fast. And a lot of this project was about bringing it back up. So I think we did that. We had a lot of problems with just, the way we allocated wasn't as fast as it could be. There were places where when we were doing our lookup change through the dynamic properties, they weren't as fast as they should be for the DOM bindings. The bindings are it's a well-known API, so you can change the way you do lookups a little bit to improve speed there. We've also looked at taking pieces of the C++ DOM and actually moving it into JavaScript. So whereas previously you would have to always be going back and forth from one language to the other, now by just moving it all over into JavaScript, you can just stay over here with a much fewer transitions back to the C++ side. Well, so one of the biggest things we had to do just when we started thinking about the project was find a good way to measure it. You can't fix what you can't measure, fundamentally. And the benchmarks that are out there for JavaScript, they're pretty good. They measure JavaScript, but they measure without changing the user interface. There is a good one from Mozilla. It's just been created in the past year, I think after we shipped Chrome is when it first shipped, but called Dromeo, and they do a nice job. We also wrote a number of internal benchmarks that we use where we'd gone around to JavaScript developers in-house and we'd said, hey, what's causing you slowness? What have you had to work around in JavaScript? And then we take a look at why the browser's slow. We put those into the benchmark. Now once they're in the benchmark, then we can finally just continue to optimize it, and things become a lot easier at that point. Hopefully you get the most important elements, the things that are most critical to go fast, are as part of your benchmark so that you're optimizing the right things. No one ever knows for sure. That's kind of the trouble of benchmarking, but we try to mitigate that by just taking lots of different things and measuring them all, and we want to go the fastest on all of them. Web pages are pretty complicated. You have a lot of different things. There's a million different things that happen in the browser. Depending on which web page you're looking at, you're going to see different potential problems. But they do all start with some common elements. Everybody's downloading content off the network. And the average size of a web page has increased by a factor of 10 over the last 10 years, right? It wasn't that long ago where people said, oh, your web pages won't be much larger than 35 kilobytes. But now you can go to CNN, you can look at almost a megabyte, and the average size is well north of 300 kilobytes. So how fast you can download that content is critical. Once you've downloaded it, a lot of it has JavaScript, which is why JavaScript has been such a heavy emphasis of Chrome. And of course, just your raw rendering engine, just how fast is it? That's why we picked WebKit to begin with, is because it did come a little bit later, after some of the newer technologies had been a little bit more established, things like style sheets and such, and it's faster doing them. So anyway, the networking is one area which is probably the biggest. It hits everybody. It varies though, because you could be on a fast network. Maybe you're on a local LAN, you've got 10 megabits straight to your computer. Or you could be on a mobile network where you've got less than 250 kilobits, and it's really kind of like a network that we did have 20 years ago. So try downloading 350 kilobytes of data over that thing, and it's going to take a while. In the last couple of years, browsers have changed a lot. Specifically, while the HTTP specification allows 2 concurrent connections to a site, up until about a year and a half ago, that was what all web browsers did. Microsoft was the first to change with IE8. They went up to 6, and all of the browsers have followed suit. That's dramatically reduced page load times. Another thing which has happened is the parallel downloading of content in JavaScript. So web pages are inherently fairly serialized. They kind of just have to go through one code path. And traditionally, when the browser discovers that it needs a style sheet or it needs a JavaScript in order to fully render the page, it might block and just stop rendering until that thing comes in off the network. And in fact, it still has to do that, but we're now a little bit smarter. So as soon as we see something which previously would have blocked us, yes, we stop and we wait for that thing to come, but while that's downloading, we continue to scan through the page, looking ahead for other things that we're going to need, and we get those started right away while we're waiting for the download. Web pages load a lot faster with that feature, and other browsers are doing that as well. For the future, we're looking at changing anything that we can in order to bring the latency down. Now with protocols and networking, you're a lot more limited. Google got its start by building fast and scalable web servers, right? And we were doing that specifically so that we could build a fast and scalable search engine. And then a couple years ago, we started on the browser. Now we've got the networking piece in the middle. And the reason the networking piece is the last to kind of get changed is because so much depends on it. You've got all the browsers already deployed, you've got all the servers already deployed. So we are looking at ways that we can change either by augmenting the protocol, but we want to do it all in an open source way and with standards bodies and such. Anything that we can do to make web pages load faster, we think is good for everyone. We've got a couple of things that we're looking at. So if you break down what a web page looks like today, it's a lot different than it was 10 years ago. So when the web started out, you had your basic HTML page, you might have a couple of images, and that was it. Today, in addition to the basic web page, you've got far more images. You've got JavaScript, you've got advertisements, you've got movies, you've got style sheets. So you might have, literally on a CNN page, you might have 150 different things to download in order to get it. And because the way the web works, we've been fairly limited in how fast we can download 150 different things. People that write their content split it across multiple domains so that browsers can make 6 connections to that domain in parallel with 6 connections to this domain in parallel with 6 connections to this domain. Some web pages will actually have 30 or 40 connections open concurrently, and that's just to work around kind of the serialized nature of the web. So can we tell the browser more quickly that it has more resources to get than what it currently does? And can we help the browser get them concurrently rather than serially? And we think we can, but that's work to be done in the future. So when we first built Chrome as a multiprocess browser, we were primarily thinking of the security and robustness properties, and how could we make the browser a really solid programming and application environment for the future. And so that's always been the first and foremost. But it turns out that there's actually some performance benefits to it as well. For instance, I told you, like, most web pages are pretty serial in nature. They can only kind of they have to do step by step by step. But by breaking it into multiple processes, we've actually got all of the web work, that is, downloading content, pulling things out of cache, that all happens in one process. And then the rendering work is happening in a different process. So you might think that, oh, well, if you're using multiple processes, you've suddenly introduced this overhead of having to communicate with those two processes. And that's true. And so a lot of what we've done is optimizing that path so that the overhead of using multiple processes is very small. But the benefit that comes out is that we can now actually get work done in parallel, whereas previously it had to be done in serial. Another performance advantage, by isolating each tab of the browser into its own process, the work being done in one tab doesn't necessarily impact the work being done in another tab. So probably we've all had experiences where maybe you've got one tab which is doing something complicated. Maybe it's Gmail and it's running some really expensive JavaScript or whatever. And you switch over to another tab, and that's the one you're trying to use now, but that other tab in the background is still getting in your way. And if you're just one process, there's nothing you can do about this. But Chrome has a couple things it can do about it. First, when that tab is in the background, we can run it at a lower priority. Operating systems have had lower priority processes forever. And so by just having partitioned, we can now take advantage of these operating system features which otherwise wouldn't be available to us. Another advantage, if you run a browser over time, it's very difficult to not have it kind of get bigger and bigger. And of course we work on that. Memory leaks are awful, and we want to keep all that to a minimum. But having a platform for robustness to avoid it is also really beneficial. So when you load a web page in one process, we have a very natural pruning point, which is when you close that tab, we get rid of the whole process, everything. Lock, stock, and barrel, it's gone. So that's where our multi-process architecture allows us to just cleave off a big chunk of work. So if you ever do have a runaway tab, if you ever do have, it's just getting too big, close down those tabs and it'll restore back to normal without having to affect, the other tabs which are running okay.